Hello everyone. Happy Tuesday, November 11th, 2025. I'm Nino, and today we're diving into the archives to pull out a really fascinating paper that's trending right now. It's all about trying to understand what's actually going on inside the brains of these giant AI models. The title is API, Accelerated Path Patching with Task-Specific Pruning. The code is we've achieved OC in 1.5442. Yeah, it's a bit of a mouthful, so let's get into it. You know, these large language models, LLMs, are everywhere now. They can write poems, code, and chat with us. But a huge problem is that we don't fully understand how they do it. They're kind of like a black box. We put a question in, and an answer comes out. But the process in the middle is a mystery. Researchers are trying to map out the circuits inside these models, which are like little pathways of neurons that perform specific tasks. Like one circuit might be for identifying names, and another might be for understanding grammar. The main tool they've been using for this is called path patching. It's a clever idea, but oh my is it slow. It's like trying to figure out how a car engine works by swapping out one single screw starting the car. Seeing what changed and then repeating that for every single screw, it's incredibly expensive and time. And that's the exact problem this paper tackles. How can we find these important circuits without spending a zillion years and $1 zillion on computing power? Oh wait, so the researchers came up with a new method they call Accelerated Path Patching, or AP for short. The idea is actually really smart and kind of intuitive. It's a two-step process. First, instead of looking at the entire massive model, they use a technique called pruning to get rid of all the unimportant parts. It's at taking that car engine and first throwing away all the screws that are obviously just for decoration or holding on the plastic cover. This dramatically shrinks the number of parts you have to check. Once they have this much smaller, leaner model, they run the old slow path patching method on just the remaining parts, because the search space is way smaller. The whole process becomes, you guessed it, accelerated. But wait, the really clever part is how they do the pruning. They didn't just choose a standard pruning method, because those can sometimes accidentally throw away really important, specialized parts of the model, and develop a new technique called Contrastive-FLAP. Here's how it works. They give a model two versions of a prompt. A clean one, where the model should get the right answer, and a corrupted one, where a key piece of information is changed or missing. For example, a clean prompt might be, when John and Mary went to the store, John bought a drink for Mary. The corrupted version might be, when John and Mary went to the store, Alex bought a drink for Mary. The key information about who bought the drink is changed. By comparing the client's brain activity on the claim versus the corrupted text, Contrast-FLAP can pinpoint exactly which circuits light up, only when the correct task-specific information is present. It finds the parts that are truly essential for the task, and makes sure not to prune them. It's a much smarter way to trim the fat. Oh, this reminds me of a joke. Why did the AI researcher bring a ladder to the lab? Because he wanted to reach the high-level abstractions. Yeah, okay, moving on. So the big question is, does it actually work? The results are pretty. This app method speeds up circuit discovery by 59 to 93%. That is a massive leap in efficiency. On average, it reduces the number of components to check by 56%. And the best part is, the circuits it finds are incredibly similar to the ones found by the original super slow method. So you're getting almost the same quality of results, but in a tiny fraction of the time. Okay, so why should we care about this? This sounds like a very technical thing for AI researchers. And making AI less of a black box has huge real-world applications. Let me give you 3 examples. First, let's talk about chatbots and dialogue systems. Imagine you're talking to a customer service bot, and it gives you a completely wrong answer. Right now, it's hard for developers to know why it messed up. With a tool like app that could quickly look inside the things in brain and identify the exact circuit that caused the error. This would make it way easier to debug and improve these systems, so they become more reliable and helpful. Second, think about information extraction and text summarization. If you ask an AI to summarize a long legal document for you, you need to trust that it's not making things up or missing a critical clause. By understanding the circuits responsible for finding and summarizing facts, we can build tools that are more trustworthy. We can verify that the AI is using the right logic, and not just guessing based on statistical patterns. And third, this is big for machine translation. Translating between languages is full of nuance. A single phrase can mean different things in different contexts. If a translation is bad, a tool like app can help developers see if the model failed to activate the correct human text-sensitive circuit. This would help them fine-tune new models to capture more of that human nuance, leading to more accurate and culturally appropriate translations. So how does this new method compare to what was out there before? Well, the paper directly compares it to two other approaches. First, what if we just use pruning by itself? The researchers found that pruning alone isn't enough. It makes the model smaller, sure, but the parts that are left aren't the clean, minimal circuit that researchers are looking for. It leaves in a lot of extra junk. And compared to the original path patching method, well, app is just path patching on steroids. It's the same core idea, but by smartly reducing the search space first. It makes the whole process practical for today's massive AI models. It's a game changer for efficiency. So to wrap it all up, this accelerated path patching method is a huge step forward in our quest to understand AI. It doesn't just find the circuits. It finds them fast enough to be useful on the models we use every day. By making this kind of analysis, known as mechanistic interpretability, scalable and efficient, it opens the door to building safer, more reliable, and more trustworthy AI systems for everyone. Alright, that's all for today. Super fascinating stuff from the archives. Thanks for tuning in, and I'll see you next time.